Good evening, students. Today we are going to start the second part of the chapter Tangent Properties of Circles. It is the second part of the chapter. What is that? Intersecting chords and tangents. Right? Let us start. Consider the circle with center O, and consider a chord, say AB. What is the name of the chord? Already you know what is the chord. Here AB is a chord. Consider a point P on that chord. Now of course the point P is inside of the circle, that is interior point. So we will tell the point P dividing the chord into two line segments. What is that? One is AP and one is P. Of course P dividing the chord, of course the chord is line segment internally into the two line segments. One is AP and another is P. Okay? Consider another circle. Right? Center O. Now AB is the chord and produce it, say, up to P. That point here is inside the circle, the point P. Here is outside the circle, the point P. And we will follow this. The point P, of course, will lie on the produced line segment AB, produced chord AB. Okay, not here or there. Okay, of course it is on this line. Then you will tell the point P dividing the chord AB into two parts. What are that parts? AP and PB. One is AP and another is PB. Of course it is externally because of the point P lying outside the circle. Clear? Here the point P is inside the circle, so it's dividing the line AB, that is the chord, internally. And here the point P lying outside the circle, so P is dividing the chord AB externally. Clear? Now come to one theorem. I think after this clear. Consider two chords together. Say one is AB, A, B, another is C, D. Two chords intersecting at the point P. Here P is inside the circle, so P dividing both chords internally. Clear? Very good. Now we have to prove the segments for the chord AB, that is AP, product of the segments AP and PB equals to product of the segments PC, PD. Clear? You have to prove this relation when the point P lying inside the circle. That is product of the segments AP into PB for the chord AB, AP into PB equal to for the chord CD, PC, PD, PC, PD. How will you prove this? Join AC and BD. Clear? This is the chord structure. How many triangles you got here? Two triangles. What are the triangles? One triangle is APC. Another one is PDB. And what are the relations between these two triangles? Can you tell? Yes. One is clear. These two angles are equal. What is the reason? Why they are equal? because of these two angles are vertically opposite angles, and you know the vertically opposite angles are always equal. And another one, these angles are also equal to these angles. That is angle ACP and angle DBP. Do we know why? Can you tell why these two angles are equal? Yes, already you learned in our earlier section, that is these two angles lying upon the same arc. What is the name of the arc? AD is the arc. One angle B, another angle C. Upon the same arc, the angle B and C are subtended upon the circumference. So these two angles are equal. So for these two triangles, two angles are equal. Angles are equal. So by using AA property of similarity, you can tell these two triangles are what? Similar. Very good. So you can write triangles APC similar. This is the symbol is similarity. Triangle PDB. You got this. If two triangles are similar, then we can tell their corresponding sides are what? Proportional. Right? Proportional. So, what are the corresponding sides for these two triangles? You can tell PC by PB equal to PC by PB equal to PA by PD. See, sides are proportional. Okay. This implies PC into PD. PC into PD equal to PA into PB. PA into PB, PC into PB. Yes. I think clear? Good. Now, here clearly P is inside the circle. If P lies outside the circle, then what will happen? Come here. The same thing will happen. At that, P will lie outside. That is, this is the circle. Consider the chord AB and consider the chord CD. Produce AB this way and produce CD. They are intersecting at P. P lies here clearly outside the circle. So, of course, P dividing the chords AB and CD externally, right? So, you have to prove the same thing. What is? You have to prove AP into PB equal to CP into PD. Same thing will happen, though P lies outside of the circle. How will you prove this? Okay. First, you join BD and SC. This is the construction. How many triangles here? Yes, two triangles. What are the names of that? Triangles PDB and PCA. The two triangles. And it is clear for the both triangles, the point angle P is common. For the both triangles, angle P is common. So you got, and another angle is read here to prove equal, for proving similarity, similar triangles. Okay, how will you prove? Here ABC ABC is a cyclic quadrilateral. Clear? Right? Cyclic quadrilateral. For a cyclic quadrilateral, there is a property. The opposite angles are supplementary. That is, if you consider this angle is x degree and this angle is y degree, then x plus y equal to what? 180. Right? This implies what? X equal to 180 minus y. 180 minus y. And yes, I think you got the answer. What is the value of this angle? Since it is a straight angle at D, straight angle. So what is the total? 180. This portion is y degree. For this part, 180 minus y. Right? So this angle is 180 minus y. And this angle, this x equal to what? You got 180 minus y. Therefore, this angle equal to what? This angle. So, in triangle APC and BPD, angle P is common and the angle PAC for the bigger triangle and for the small triangle PDB are equal. So two angles for the both triangle, two angles same by using AA property. Triangle what? ACP similar triangle BDP. Right? Interesting, no? Right. So, you can tell the corresponding sides are what? Proportional, since two triangles are similar. So, how do you write? For the smaller triangle, consider PB. PB by the bigger one, PC. Equal to, for the smaller one, PD. For the bigger circle, PA or AP. No problem. This implies multiply PB into AP equal to PC into PD. PA, PB as put. Clear? There is another theorem. Let me draw first. Okay? Here, AB is a chord produced up to P, and PT is a tangent at the point of contact T to the circle centering at O. All are from the outside point P. Okay? So, of course, exterior point dividing the chord AB externally into two line segments. What are they? One is AP, another one is PB. Right? What to prove? You have to prove the product of the line segments divided by P, that is AP into PB equal to the square of the lengths of tangents P T square. This is the theorem you have to prove here. That is, the product of the line segments divided by the exterior point P, PA and PB is equal to the square of the lengths of the tangent from the outside point P to the point of contact at T of the circle centering at O. You have to prove this. How will you prove this? Okay, let us start. Here OT is the radius at the point T, that is to the point of contact of the tangent PT. So of course, what will be this angle? Right angle, because of already we learned radius always remains at right angle to the tangent at the point of contact, right? And draw a perpendicular from the center to the chord AB. Perpendicular. Say it is D at the point D. OD is the perpendicular at the chord AB. So of course the length DA and DB will be equal. You know this. That is DA equal to D. Join OB, the radius, OT, the radius are same in length, since radius of the same side. Also join OP. These all are in construction part, right? Yes. Complete? Let us prove. AP into PB equals to AP, that is this length, and PB, that is this length. AP, the total length, can you write AP is equal to AD plus DP, understood? AD plus DP, that is AP, into, in place of PB, PB, that is PD minus DB. Understood? This is PB. PB, that is this length, that is total length. From the total length, if you minus DB, then you will get PB. Clear? I think clear. AD equal to DB plus DP, okay, into PD minus DB. If you write this way, DP plus DB into DP minus DB. Understood? DB and DP are same length. A plus B, A minus B. Understood? What is the formula from algebra? Yes, A square minus B square. So you can write DP square minus DB square. Clear? Good. DP square minus DB square. Now come to the figure. DP square, DP square minus DB square. So what is DP square? What is DP square? From the triangle DOP, always you will follow the figure step by step, okay? Don't go without figure. DP square. DP is the base, DO height, and OP is the hypotenuse for the right angle triangle OPB. See carefully, okay? So DP square is equal to, can you DP square OP square minus OD square. Clear? Again, the triangle OBD also right angle. At right angle at D. So in place of DB square, you can write OB square minus OD square. I think clear? This is equal to OP square minus OD square minus OB square minus plus OD square. OD square cancelled. OP square minus OB square. Again come to the figure. OP square and OB square. OB square, that is radius of the circle. We can write OB is equal to OT. In place of OB, we can write since they are same in length. So OP square minus OB, that is OT square. What is this? Now come to the right angle triangle OTP. OB is the hypotenuse, TP is the base, and OT is the height. So OP square, that is hypotenuse square minus height square, is equal to what? Base square, that is PT square. What to prove? PT square. PT square. Already we proved. Understood? So always you follow the figure. From the figure, step by step it will come automatically. Understood? Good. We have to prove another theorem. This is the last theorem for intersecting chords and tangents. Last theorem. After proving that theorem, we will go to the exercise. Okay? Let us draw the theorem first. Here, ABC is a triangle inscribed in a circle centering at O, and PQ is a tangent to the point of contact at C, to this circle. We have to prove angle BAC equals to angle QCB and angle CBA equals to ACP. These are called alternate segment angles. You have to prove this. Okay. First come to this part, that is angle BAC equal to BCQ. Let us assume this is x degree and this is y degree. That is you have to prove equal to y. This angle is equal to this angle. Right? Angle x equal to angle y. How will you prove this? Let us start. There is some construction. Draw the diameter to the center O. So it is D join also DB. Clear? Now of course it is clear the angle DBC is right angle. DBC right angle. What? It is the angle subtended on the circumference upon diameter. This is the diameter. Since the chord through the center O. So it is the diameter and the angle B here, right angle. One more thing. Since radius always remains at right angle to the tangent at the point of contact, so this angle also what? Right angle. Clear? Now, one more thing here. The angle CAB equals to what? CDB. Because of what? Both angles subtended upon the circumference on the same arc CP. Clear? So if this angle will be x, so of course this angle also will be x. Clear? Now what will be the value of this angle? Since the triangle BCB, B angle is right angle, this angle is x, of course this angle will be 90 minus x. Clear? Again, angle DCQ is equal to what? 90 degree. And from here, what is the DCQ? Y plus 90 minus x equal to what? 90. This implies y plus 90 minus x equal to 90. From both sides 90 cancel, y minus x equal to 0. This implies x equal to. Let's prove that is this angle, that is y equal to x. Similarly, you can prove the second part, that is if this angle be z, this angle also will be z. Understood? Good. So next we'll try to solve some problems, okay, from this chapter of the exercise. Okay.